So for this section, I'm going to talk about sort of office hour questions that people posted on the forums. So I'm really glad people put all sorts of questions and discussions, whatever, and I'm sorry I can't talk about all of them. I just had to pick some of them. And I made this kind of simple outline of what I'm going to say. So the most popular topic, in a sense, was, well, what can I do after CS 101? What should I go? What about this language, that language, whatever? And I'm not going to answer that right now. That'll be, I promise, I will talk about HTML5 and phone programming and Java and Python, all those sort of things. I will talk about in the last week. We'll have an official section about that. So I'm not talking about that today. So that gets rid of like half the questions. So other than that, I'll just go through some I chose out that seemed interesting. So Margaret Imber asks, essentially, well, how do you produce this stuff? What kind of goes into it? First off, I should say, I feel like the technology, I mean, it works, but I also feel like the whole online education area is so hot that I'm sure 10 years from now it'll be just light years better. But the way that CS101 is produced, I think, works pretty well, and it's actually fairly simple. So I write, for each lecture, I just write straight HTML, which is the sort of standard language of web pages. And there's a thing called CSS that's used to kind of style web pages and set the fonts and colors and stuff. And then I just have JPEG and PNG images, which are also standards, and I put those in the pages, and that's the web page. So that's what the lecture documents look like. There's a program called OpenOffice, the free Office suite, or recently there's a new version of it called LibreOffice, which is like, talk about nerds coming up with not good product names. I think LibreOffice is not a good name, but anyway. That includes a free draw program, and so that I just use the free program to produce the rectangles and boxes and whatever. Just as an aside, I will mention, if you're ever producing a document where you're trying to explain something, man, diagrams are just so awesome. And I think a lot of authors or teachers feel sort of inhibited, like, oh, well, I'm not going to make very good art, it's not going to look that great. And so they're sort of inhibited to where they just don't do it, or in words, they end up trying to paint a picture in words of what the thing is. And I got to say, just make a diagram. Just use your crummy art skills and don't feel inhibited about being criticized, and just make a simple little diagram, and it's much better. Anyway, that's what I do. So that's how you end up with these fairly crude-looking diagrams sprinkled all through here. So just in terms of producing the videos, I was thinking, like, sometimes you'll hear a story where someone say, oh, well, I had this tire in my car and it blew up and I was almost killed. And you're like, oh, what kind of tire was it? And they'll say, well, I don't want to say. Well, that's lame. Whatever. We should give credit or criticism where it's due. So I'm just going to say what technology we've used here. I actually have a little picture. So to produce the videos, here's our picture. So this is what a typical setup looks like. So I'm sitting on a laptop, and I've got here the HTML page open. I'm just going to, and obviously I just sort of scroll through it as I'm talking about stuff. So for the sound, there's this company Blue that makes a bunch of microphones, these USB microphones that just plug into your computer, and so we've been using that. Seems to work pretty nicely. And then the video of the talking head is just this Logitech HD camera, which also seems to work very nicely. It's also USB. So those just plug in here. And then finally, on the Mac, we use a software called ScreenFlow that seems, it's pretty easy to merge together the picture of the desktop, showing the computer screen, and merging in the talking head and the sound, and that works very nicely. So I'm pretty happy with that. All right, so yeah, that's how we produce it. I should say then Coursera has its own kind of internal technology for how it does the exercises and whatever, and I'm sure that's going to change a lot and get better, but it works. All right, another question. We have Roberto Lopez asks about nested if statements and or logic, sort of a natural, from last week. This is kind of a natural question. It's a great question, really. It turns out that's the topic this week. You're going to see all sorts. So it turns out the syntax for that is this and or business. That's in the so and is to ampersands, or is to vertical bars, and that's all through this week's lectures, and it'll come up more than you want on the end of week exercises. So that's a good anticipatory question there. Oh, also just nested if statements, putting one if statement inside of another. Turns out it's kind of like and, because you end up having the first test and the second test have to be true. So anyway, let's check that out. Another question was about syntax, computer language syntax. So Mervin Villanueva asked a question about syntax, and some other people mentioned it. So I know that in CS101, sort of going from no programming to some programming, the syntax maybe is it's very sort of in your face of like, gee, this is kind of annoying. And I'll tell you, all computer languages have this sort of fixed syntax. And ultimately, I think it is not an accident that the fixed, sort of rigid syntax is ultimately an excellent way to communicate with computers. So honestly, I don't see that going away. You get used to it. I work with computers all day long, all sorts of different syntaxes, and I never feel like, oh, this syntax, oh, it's really interfering with my ability to express my ideas. You know what? It's like at some point I just got used to it. That's how computers are, and now I just work within that system very comfortably. So I don't know if that's regarded as good news, but that's my honest take on the system of syntax. Chris Prosser points out there's a system called Scratch that enables you to do some sorts of programming, but without syntax, where you sort of drag and drop these little blocks around that represent logic. There's also the somewhat famous Alice system, where you have these 3D things that kind of run around, and that also doesn't use syntax. So those are experiments in this kind of programming space. Well, could you show people something about logic? Let them play around and learn about computers, but not get bogged down in syntax. Realistically, my take is different from the Scratch and Alice systems, where my take is that very introductory students can deal with a little bit of syntax. I mean, that's my attempt at this problem. But these non-syntax systems are very also popular. It's just, I don't know, you have to kind of jump through a lot of hoops and stuff to make things work without syntax. So ultimately, I put my bet on, let's try and make syntax work. And then honestly, it remains to be seen which way works better. I mean, obviously, it's just going to be different for different audiences. If I had first graders, I would think, maybe the syntax is too much. Maybe I would try something else. But anyway, this is a current area of research, how that's going to work out. Anonymous person asked, what is the real syntax for a JavaScript for loop? So I've mentioned here and there, I should do this in the last lectures as well, that mostly we're doing JavaScript, but you've got these sort of Nick extensions on the front of them. So at the end, I'll need to expose what it is I've been helping you with there. So all computer languages have some syntax for this idea that you have a big group of things and you want to just essentially loop over them, right? You want to do some operation for each one. So here's a good syntax for that. For pixel colon image. That's the syntax we've been using. And actually, that is pretty much the syntax that Java uses, and actually very close to the syntax that Python uses. And those are two very popular languages. It happens, ironically, this is not the syntax that JavaScript uses. JavaScript, just by historical accident, doesn't have a good syntax for this very common case. And I think this is one of the very unfortunate things about JavaScript. Now, you might ask, well, geez, why don't they just fix it? It's a little bit, once a language is out there and millions of lines of code have been written, they can't just change and say, oh, well, let's work. So it's sort of like if England decided, it really would be better if we all drove on the right-hand side of the road. Yeah, but they've got all these roads and all these cars. There's all this stuff in place where they can't just switch. And so when I say something is sort of stuck as a historical accident, that's what I mean. And it happens that JavaScript, history was unkind. It has many nice qualities, but this one is terrible. So anyway, what is the syntax? So the syntax begins for I, or this could be any variable you want, for I in image. So you're going to loop I over image. But unfortunately, in this case, you would think I was going to be the pixels themselves, but it's not. It's an index into the image. And so then your next line would have to say pixel equals image square bracket I. So you take this index you've gotten here, you use it in the square brackets on the image, and then that gets you the pixel out. Anyway, obviously this is not going to come up for CS 101, but that's the syntax. There's a couple syntaxes in JavaScript, but that's probably the best one. Now, if you're writing a lot of code in JavaScript, I'm a little saddened by this kind of lame syntax, but you know what? Whatever. Looping over stuff is very common, and within a day, you could just get used to like, okay, well, that's how we have to do it, and whatever. That's not going to be a big bear. You could manage that. All right, another question I really liked from Dave Pittman and Chris Prosser was this question of, well, if you have a 0 or a 1 or whatever in the computer, how does it know if it's a part of a JPEG, maybe it's part of the red color, or it's a letter in an email or something? How does that work? So the way it works, I drew a little picture here, is you can think of RAM there are billions of bytes in RAM, and the bytes are just laid out in an unmarked uniform field. It just starts at, the 0th byte, runs all the way through the end, and there's no distinctions about anything. They're just all bytes. So the way it works is that the software which is manipulating RAM lays it out by area and the software knows which bytes it's going to use for which purposes. So let's say here's this big bunch of bytes, and so let's say I'm in a byte. My example was it could be part of an RGB image, or maybe it's a single typed letter. So let's say it's a single typed letter. So maybe the program it has all this RAM, and it'll say, well, these bytes here, there's 10,000 bytes or something. It says, I'm going to use these bytes to hold an email that someone is typing in. And so it could sort of do it by area. It sort of marks off that area and says, this is an email here. So then as the user types in the letters of the email, so the letter A is something and the letter T is something or whatever, then maybe those bytes get set in here. It sets the zeros and ones to be the number for the letter A or the letter T or whatever. And so then later, when the software looks at this area, it knows, oh right, this is the area I set aside for email, so I know to interpret these bytes as letters. Or alternately, you can imagine if the program said, okay, I'm going to store a big RGB image here. That's what I'm going to use these bytes for. And that's a little more complicated because it would even need to know, well, what's the scheme? So the scheme usually is that it's going to have the red number followed by the green number followed by the blue number for each pixel. So it'll sort of follow this three bytes at a time pattern. And I'm glossing over some other details there. So it would know that maybe that's a red number, 0 to 255, and then it would know that maybe that's the next red number. So the point here is that if you look at the chips, the bytes, it's just undistinguished, so it seems to give you no toehold. The way the software is able to work coherently is essentially by having a pre-plan about, for this area of bytes are going to be used in such and such way, and then just by being consistent with that plan when setting the bytes and then later when reading them back. You could also say, in a way, the hard disk, the flash memory, it's all sort of the same, right? That the hard drive, likewise, it pretty much just looks like a big bunch of bytes. And so the software would need to know, oh, something other file.jpg. Oh, I know that in that I stored the bytes of an RGB image or something. So it needs to have some plan so that when it gets the bytes back, it knows how that they're organized. All right. So, all right, so here goes our last question. So it's sort of a broad question of, well, what does it take? What would you want to do if you want to be a CS major? Salvador Diaz. So I'm going to have a somewhat long-winded answer to this question. So the first thing you should know is that most colleges do not require, if you want to major in CS, don't have some requirement that you come in with programming ability. So, for example, at Stanford, the Stanford CS 106A course, it's an excellent course. It's fairly difficult, but there's an enormous amount of support. There's tons of office hours and all this help, so people of a lot of different abilities can all get through it. That course requires no experience whatsoever. So you just show up, and then that is a full programming course. So CS 101 is not a full programming course. It's kind of a sampler. I'll describe this more in the last week. But 106A is a for real, pretty demanding real programming course, 10 weeks. So what does this mean if you're pre-college and you're just sort of thinking about this? Well, one answer, and I talked to a couple of colleagues at Stanford about this. Well, one answer is, well, you just want to kind of do well in math and science and English or whatever, just courses that colleges look at just to get into college at all. That's maybe a good background goal. Now, I'm going to take that apart a little bit and say, I don't think it is that important in particular that you do well in math or science to take CS. That's maybe slightly controversial. Obviously, computer science involves doing some math and sort of organized logical thinking. But if you happen to hate biology, or actually even if you dislike calculus, I don't see that as being a big problem for CS. I think computer science, in some sense in CS 101, you've gotten a real sense of what the sort of, there is math and there is logical thinking, but I think it's a little bit of a thing unto itself. If someone has done very well in calculus or very well in physics, I mean, that's fine. I mean, it just shows that their brain is good at working on stuff, and that's going to be useful for computer science. But I think it is more sort of a historical accident that physics, or sort of at my high school, calculus was regarded as this very important advanced thing to do. Whatever. I mean, it's fine. You get to use your brain and you practice something interesting, but I wouldn't link it to computer science exactly. So, what is going to help you with computer science? I'd say the most important thing for computer science, and not everyone agrees with this, but I feel it's true, is programming experience. Like playing, and programming doesn't have to be some big heavyweight thing, but I think playing around with computers in a meaningful way gives you a stronger intuition about how they work, what the boundaries are. And obviously CS 101 very much fits into this pattern. So there's many things that you can do with computers that I think help sort of fill in those instincts. I think the key feature is having some sort of real project. You're typing and clicking on the computer, creating something that when you play with it has some visual output, and then you can change it in some way and then get slightly different output. I think those are the key qualities. It's possible for someone to just self-motivate, like get the book on whatever and then play around on their own, but I think that's difficult. In a sense, this is why courses exist. Like, well, even if maybe you had the ability to play around with the robot or whatever, it's just much easier if there's someone setting kind of a weekly cadence and giving you little goals that are sort of spaced out appropriately. So that said, I'm just going to mention a bunch of sort of computer-related things that I would think would be useful, or if I was talking to a high school person who was interested in maybe doing computer science. Just sort of in no particular order. So there's a chip I showed earlier, the Arduino. Arduino is set up for doing essentially little art projects with little blinking lights or switches or whatever. So it's a physical thing. It's not software just on the screen of your computer. And there's a lot of books and kits and whatever, essentially to play around with the Arduino. It's kind of fun. It has a sort of a hands-on feeling, and it involves a little bit of programming. So that's a neat random thing, something to play with. There is, in the US, I don't know if it's international. I'm not sure. There is a computer science high school course. It's in Java. It's a fine class. There's lots of books and online resources or whatever that happen to fit in the material, and some high schools have it, but some don't. I mean, I think that's why colleges realistically should not expect some prior experience, because whatever, you could have a great, the world's greatest high school student, but whatever, their high school just didn't have it. A lot of high school people play around with robotics. It's sort of like the Arduino. It's kind of a fun, hands-on way to play around with computers. I came up with a couple of sort of weaker forms. Spreadsheets, you may have heard of spreadsheets. Spreadsheets actually have in them a simple language. For the Google spreadsheet, it is actually JavaScript, which allow you to write little short bits of code, but that do real interesting manipulations with data, adding things up or computing something you want to compute. So next time you find yourself in a position where you've got some big ton of data, for part of your biology class or some club or something, I would say, well, be open to, oh, you know what, I'm going to go read the docs and actually try and use the spreadsheet to do this rather than doing it by hand or something. I think that is an example of pushing yourself to use the computer in something that looks like code that I think is that helps to fill out that skill set to sort of make stuff work. Another sort of fun example is some games have a level editor. That's maybe a kind of a reduced form of programming, but the level does have a kind of a logic to it, and so you could play around with the level editor and then play it and sort of see, yeah, sure. I think that is giving you some insight about the formal structure of computers. So yeah, as I said, anything where you're using your brain and seeing the results and doing adjustments, I think is good preparation for doing stuff with computers. Alrighty, so thanks again for all the people who sent in questions. Like I said, I'll have the what could you do after CS 101 will definitely be a last week topic. All right, take care.